Hello viewers. Today we are going to study the t-test. Now this t-test I will be teaching you in two sessions or two parts, part 1 and part 2. In part 1 I will be taking the t-distribution and one sample t-test. In part 2 I will be covering two sample t-test and the paired t-test. So before going forward in detail, let's understand what is a t-test. As it is also known as student's t-test, it is a tool for evaluating the means of one or two populations using hypothesis testing. So a t-test may be used to evaluate whether a single group differs from a known value, that is one sample t-test, or whether two groups differ from each other, that is an independent two sample t-test, or whether there is a significant difference in the paired measurements, that is a paired or dependent sample t-test. Now the question arises in our mind, how are the t-tests used? So first we can define that what is our hypothesis, so which we are going to test, and then we can specify what is the acceptable risk of drawing a faulty conclusion, that means accepting a faulty hypothesis. So for example, when comparing two populations, we might hypothesize that the means are the same, and we can decide on an acceptable probability of concluding that there is a difference exists when that is not true. So now we can also calculate a test statistics from the data and compare it to a theoretical value from the t distribution. So depending on the outcome, we can either reject or we can accept or we can fail to reject our null hypothesis. Now the question arises again, what if I have more than two groups? Of course, we can use t-test, but we cannot use t-test when we have more than two groups. Then in that case, we can use multiple comparison method. Examples are like analysis of variance, ANOVA. We can use Tukey-Kramer pairwise comparison. We can use Dunnett's comparison to a control and analysis of means, that is ANOVA. How to choose the correct test? So here I have given the table which summarizes the characteristics of each and provides us the guidance on how to choose the correct t-test. Now we can also see that various t-type tests which are available on the, you can say, websites. You can go through it and you can see the assumptions and the calculations in detail, which I will also be covering in my coming sessions. So as we can see here in the table, we have student t-test, so food sample t-test and the pair t-test. So when the number of variables is 1 and we use one sample t-test, when the number of variables are 2, we use two sample t-test, and in pair t-test also we have two variables. We can also identify which test to be, we can say, taken for the calculation, and that we can decide on the basis of the type of the variables which are available in our, you can say, data collection. And then we can also decide on the basis of the purpose of the test. What is the purpose? Like if we want to decide if the population mean is equal to a specific value or not, we will use one sample t-test. If we want to decide if the population means for two different groups are equal or not, we will use two sample t-test. And if we want to decide if the difference between the paired measurements for a population is 0 or not, we can use the pair t-test. Similarly, we can see if we want to estimate population mean and we want to have sample average, so we will use one sample t-test. If we want to have sample average for each group, we may go for the two sample t-test. And if we want to have sample averages for the differences in the paired measurements, we may go for the paired sample t-test. Another very important, you can say, parameter which can decide which t-test to be used is the population standard deviation. So if population standard deviation is unknown, so in single, you can say, single sample t-test, we will use sample standard deviation. And for two sample t-test, we will use standard deviation for each group. And for paired t-test, we will use the sample standard deviation of differences in paired measurements. Same way, degrees of freedom. Okay, so it is what number of observations in sample minus 1. So in single sample t-test, we will be using it as n minus 1. But if we are adopting two sample t-test, in that case, it is n1 plus n2 minus 2. So that is the degree of freedom. While in a paired t-test, we take it as n minus 1. That is the number of paired observations in sample minus 1. So from this table, we can easily see that the t-test for the populations and another common t-test is for correlation coefficients. So we can use the t-test to decide if the correlation coefficient is significantly different from 0 or one-tailed versus two-tailed test. So when we define the hypothesis, we also define whether we have one-tailed or two-tailed test. We should also make this decision before collecting our data or doing any calculation. So we make this decision for all the three of the t-tests for means. Now, to explain, let's use one sample t-test. Suppose we have a random sample of protein bars and the label for the bars advertises 20 grams of proteins per bar. Now, the null hypothesis is that the unknown population is 20. Now, suppose we simply want to know if the data shows we have a different population mean. So, in this situation, our hypotheses are that null hypothesis says mu is equal to 20, and alternate hypothesis says that mean is not equal to 20. So, here we have two-tailed test. We will use the data to see if the sample average differs sufficiently from 20, that is either higher or lower, to conclude that the unknown population mean is different from 20. Now, suppose instead that we want to know whether the advertising on the label is correct. So, does the data support the idea that the unknown population mean is at least 20 or not? So, in this situation, our hypotheses are that null hypothesis will be that mean is greater than or equal to 20, while alternate hypothesis says that mean is less than 20. So here we have one tail test. We will use the data to see if the sample average is sufficiently less than 20 to reject the hypothesis that the unknown population mean is 20 or higher. So after understanding all the details about the hypothesis and the test, now the question arises how to perform a t-test. So to perform a t-test, it involves means. So we have to perform the steps in analysis. So the first step is to define our null hypothesis and alternate hypothesis before collecting our data. After collecting the data, we should decide upon the alpha value. That means this will involve determining the risk we are willing to take of drawing the wrong conclusion. For example, suppose we set alpha to be 0.05 when comparing two independent groups. That means we have decided on a 5% risk of concluding the unknown population means are different when they are not. So once the second step has been done, that means our alpha has been decided, we need to check the data for errors. So now, once we have checked the data and we have made the data error free, the next step is to check the assumptions for the t-test. Once the assumptions like the normality, homogeneity and all has been checked, the next step will be to perform the test and draw our conclusion. So all the t-test for means involve calculating a test statistics. So we compare the test statistic to a theoretical value from the t-distribution. I will be taking the t-distribution in detail. The theoretical value involves both the alpha value and the degrees of the freedom for our data. So as I was telling you that I will be taking the t-distribution, first let's understand what is t-distribution. The t-distribution describes the standardized distances of sample means to the population mean when the population standard deviation is not known. And the observations come from a normally distributed population, which we have already taken this as a assumption for t statistic. Now the next question arises, is the t distribution the same as the students t distribution? Yes, somewhere we use students t distribution, and in some cases we use the simple t distribution. So what is the key difference between the t and the z distributions, which we have already discussed in the previous session? See, the standard normal or the Z distribution assumes that we know the population standard deviation, and the T distribution is based on the assumption that we have the sample standard deviation. So T distribution versus the normal distribution. As we can see over here in the graph, the normal distribution. Okay. So the T distribution is similar to a normal distribution. It has a precise mathematical definition. And instead of involving too complex maths, we can see over here the useful property of the T distribution. And this is why, like, what is the important in the analysis. Like the normal distribution, the T distribution has a smooth shape. Like the normal distribution, the T distribution is symmetric. So if we think about folding it in half at the mean, each slide will be the same. Like a standard normal distribution or Z distribution, the T distribution has a mean of 0. So the normal distribution assumes that the population standard deviation is known, while the T distribution does not make this assumption. So the T distribution is defined by the degrees of freedom. These are related to the sample size. The T distribution is also most useful for small sample sizes when the population standard deviation is not known, or it can be both the cases. So we can see that the sample size increases. If then the T distribution becomes more similar to a normal distribution. So considering the graph which is there on the screen, you can compare the three T distributions with a normal T distribution. As you can see, the pink lines, it is like distribution with 1 degree of freedom, while the blue line shows T distribution with 2 degrees of freedom. The yellow line shows T distribution with, you can say, 10 degrees of freedom. And this green line is the standard, or you can say, or the normal distribution, which we uses for the Z test. Now, as we have seen, all the distributions have a smooth shape and always they are symmetric. All have a mean of 0. So the shape of the T distribution depends on the degrees of the freedom. The curves with more degrees of freedom are taller and have thinner tails. All three T distributions have heavier tails than the Z distribution. You can also see how the curves with more degrees of freedom are more like a Z distribution. So we compare the pink curve with 1 degree of freedom to the green curve for the Z distribution. The T distribution with 1 degree of freedom is shorter and has thicker tails than the Z distribution. When we compare the blue curve with 10 degrees of freedom to green curve for the Z distribution, these two distributions are very similar. So a common rule of thumb is that for a sample size of at least 30, one can use the Z distribution in place of the T distribution. And figure also shows that T distribution with 30 degrees of freedom and a Z distribution. So the figure uses a dotted line, green curve for Z, so that we can see both the curves. So this similarity is one reason why a Z distribution is used in statistical methods in place of the T distribution when sample sizes are sufficiently large. Now coming to the tails for hypothesis test and the T distribution. So when we perform a t-test, we check if our test statistic is more extreme value than expected from the t-distribution. So from a two-tailed test, we look at both the tails of the distribution. So here the figure shows the decision process for a two-tailed test. The curve is a t-distribution with 21 degrees of freedom. The value for the t-distribution with alpha zero point zero 0.05, so that is, it is a two-tailed test, so it will become 0.025 on both the sides. So the value is of the t-distribution for 0.025 is 2.08. So for a two-tailed test, we reject the null hypothesis if the test statistic is larger than the absolute value for the reference value. If the test statistics value is either in the lower tail or in the upper tail, we reject the null hypothesis. So if the test statistic is within the two reference lines, then we fail to reject the null hypothesis. So how to use a t-table? That is again a very important question. So most people, when use software to perform the calculations needed for the t-test, but when we use statistics book, we can use t-tables. In software, we need not go for the values. So understanding how to use a table might be useful only when we are using it book statistics. So that step below describes how to use a typical t-table. Step 1, identify if the table is for two-tailed or one-tailed test. That we have to see first. Then we decide if we have one tail or two tail. Then accordingly, the column for the t-table we identify and the different alpha levels. So if we have a table for one tail test, we can still use it for two tail test. If you like setting our alpha to be 0.05 for two tail test and have only one tail table, then we can use the column for alpha is equal to 0.025. So then second step is to identify the degrees of freedom from the data. Then the rows of the T table correspond to different degrees of freedom. So most tables goes up to the 30 degrees of freedom and then stop. The table assume people will use Z distribution for larger sample sizes. Third step, we will find the cell in the table at the intersection of our alpha level and the degrees of freedom. So this is the t distribution value, and then we compare this statistic to the t distribution value and make the appropriate conclusion. So now let's do one sample t-test. So first let's answer the question, what is one sample t-test? One sample t-test is a statistical hypothesis test used to determine whether an unknown population mean is different from a specific value. So when can you use this test? You can use this test for continuous data. Your data should be random sample from a normal population. What if the data is not normally distributed? So if the sample sizes are very small, you might not be required to test for normality, but you might need to rely on your understanding of the data. So you cannot safely assume normality. So you need to perform a non-parametric test whenever we are not able to assume the normality. Okay. So now using the one sample t-test, now we need to test and check our data, and then we will be performing the test and understanding the test results and statistical details. So for one sample t-test, as I have already told you, we need one variable, and we also should have an idea or a hypothesis. That is, the mean of the population should have some value. Let's see with one example. Like a hospital has a random sample of cholesterol measurements for men. These patients were seen for issues other than the cholesterol. They were not taking any medications for high cholesterol. The hospitals want to know if the unknown mean cholesterol for a patient is different from a goal level of 200 mg. So as we measure the grams of proteins for a sample of energy bars, This is another example. The label claims that the bars have 20 grams of proteins. Now we want to know if the labels are correct or not. One sample t-test assumptions we have already discussed. So for a valid test, we need data values that are independent. That means values are not related to one another. Then values should be continuous and they should obtain via simple random sample from the population. Also, the population is assumed to be normally distributed. So, like imagine that we have collected a random sample of 31 energy bars from a different stores to represent the population of energy bars available to the general consumer. So, the labels on the bars claim that each bar contains 20 grams of proteins. Now, as we can see here in the table, it is given energy bars are given and the grams of proteins are given. So if we look at this table, we can see that some bars have less than 20 grams of proteins and while others have more. So we might think that the data support the idea that the labels are correct, but others might disagree. So the statistical test provides a sound method to make a decision so that everyone makes the same decision on the same set of data values. So now let's check the data. So for that, the first question that needs to be answered is the t-test an appropriate method to test that the energy bars have 20 grams of protein? Okay, so for this, we can have the checks for the test. The data values are independent. Let's see. The grams of the proteins in one energy bar do not depend on the grams in any other energy bar. So example of dependent values would be if you collected energy bars from a single production lot. A sample from a single lot is representative of that lot. So not energy bars in general. So here we can say that the data values are independent. Let's check another check, that is the data values are grams of proteins. So the measurements are continuous. Then we need to assume that the energy bars are a simple random sample from the population of the energy bars available to the general consumer. That is a mix of lots of bars. So we assume the population from which we are collecting a sample is normally distributed. And for large samples, we can check this assumption. So we decide that the t-test is an appropriate method. So before jumping into analysis, we should take a quick look at the data. The figure shows a histogram and summary statistics for the energy bars. So from this diagram, let's have a quick look at the histogram, and we can see that there are no unusual points or outliers. So the data look roughly bell-shaped. So as our assumption of a normal distribution, okay, as you can see here, if you see, it is going like this, okay. So it is taking a normally a bell-shaped curve, okay. So our assumption of a normal distribution seems reasonable. Now from a quick this thing statistics, we can see that average is 21.40. So that is, you can see, above 20. Okay. So does this average from our sample of 31 bars invalidate the label's claim of 20 grams of proteins for the unknown entire population mean or not? That is what is to be answered. So let's perform this one sample t-test. So for the t-test calculations, we need the average, standard deviation and sample size. So here we can see in the summary statistics uh, and the formula. So we round the statistics to two decimal places. Software will show more decimal places and use them in calculations, but we here have taken only two decimal places so that the actual data used to calculate the summary statistics might have more places. Now we start by finding the difference between the sample average and the 20 which we have taken as a null hypothesis. So here we can see 21 minus 40 minus 20, that is difference is 1.40. Okay, so next we calculate the standard error for the mean. So the calculation of the standard error for the mean is uh, standard deviation upon under root n. So 2.54, that is the standard deviation, okay, divided by uh, under root n, so the value comes to 0.456. Now this matches the value in the figure. So we now have the pieces of our test statistics. We can calculate our test statistic like t is equal to difference upon the standard error. So our difference is, here you can see 1.4, okay, and the error is 0.456, so the answer comes to 3.07. Now, to make our decision, we compare the test statistic to value from the t-distribution. Okay, now this finding the value from the t-distribution may involve certain steps. So we calculate the test statistic. Our test statistic is 3.07. Then we decide on the risk we are willing to take for declaring a difference when there is not a difference. So for any energy bar data, we decide that we are willing to take 5% risk of saying that the unknown population mean is different from 20. So when in fact it is not. So in statistics, we say that alpha is 0.05. So in practice, setting our risk level, that is the alpha, it should be made before collecting the data. So we find that the value from the t distribution based on our decision that we need the degrees of freedom. So degrees of freedom is n minus 1, and n is the number of observation. So 31 minus 1 is 30. So after seeing the degree of freedom, we'll come to the critical value of T. And critical value is the alpha, that is 0.05, and the 30 degrees of freedom is, you can say, plus minus 2.043. So here is most statistics book, they look for tables for the T distribution. We can also find tables online. So the most likely situation is that we will use software and will not use the printed tables. So after seeing to this, we can compare the value of our statistics, that is 3.07, to the t value. And that t value we can see is 2.043. So since 3.07 is greater than 2.043, we reject the null hypothesis uh, that the mean grams of protein is equal to 20. So we make a practical conclusion that the labels are incorrect and the population mean grams of protein is greater than 20. Now here let's see the statistical details which has been involved. So as we have taken that the energy bar data and one sample t-test, we are using these statistical terms. Our null hypothesis underlying the population mean was equal to 20. So the null hypothesis is written as H0 is equal to mu is equal to 20. And the alternative hypothesis is that underlying population mean is not equal to 20. So the labels claiming 20 gram of protein would be incorrect. This is written as HA, that is mu is not equal to 20. Now this is a two-sided test. We are testing if the population mean is different from 20 grams in either direction. So if we can reject the null hypothesis that the mean is equal to 20 grams, then we make a practical conclusion that the labels for the bars are incorrect. And if we cannot reject the null hypothesis, then we make a practical conclusion that the labels for the bars may be correct. So as we have seen, we calculate the average for the sample and then calculate the difference with the population mean, that is x bar minus mu. And then we also calculate the standard error as standard deviation upon under root n. So making the test statistical formula, that is s x bar minus mu upon s upon under root n. So we compare the test statistic to a value t, where with our chosen alpha value and the degrees of freedom for our data. Okay, so using the energy bar data as an example, we set alpha is 0.05. The degree of freedom, as we have seen, is 30, that is 31 minus 1. And here we write that t value with alpha 0.05 and 30 degrees of freedom as, you can say, 0.05, okay, plus minus 0.05. Okay, that is how we write t. then subset 0.05 comma 30. So that is how it is written. So the t-value for a two-sided test with alpha zero point zero 0.05 and 30 degrees of freedom will be taken as you can say plus minus 2.042. So there are two possible results for our comparison. One is the test statistics is less extreme than the critical t-value. So in other words, it means that the test statistic is not less than minus 2.042 or is not greater than plus 2.042. So we fail to reject the null hypothesis that the mean is equal to the specified value. In our example, as we have seen, we will be unable to conclude that the label for the protein bar should be changed. Now, the other test statistic is more extreme than the critical t-value. So, in other words, we can say that test statistic is less than minus 2.042 or is greater than plus 2.042. So, we reject the null hypothesis that the mean is equal to the specified value. So, we can conclude that either the label should be updated or the production process should be improved to produce on average bars with 20 grams of proteins.